Right now, as you watch this, something you cannot see is passing through your body. Hundreds of unknown particles every second, possibly thousands, possibly more. They do not slow down. They do not interact with your skin or your bones or the atoms of the air around you. They have traveled across the galaxy to reach this room, and they will continue on through the Earth and out the other side without leaving any trace. We call this substance dark matter, and it makes up most of the matter in the universe. We do not know what it is. By the end of this video, you will understand why physicists are so certain that it exists, what it does not do, and why the search for it has become the largest unsolved problem in modern science. If you find these reflective explorations of the cosmos meaningful, a like or a subscribe helps us continue making them. Point a telescope at the nearest large galaxy, Andromeda, 2.5 million light-years away, and you can see about 1 trillion stars arranged in a slowly turning spiral. The light from those stars has been traveling toward Earth for longer than there have been humans to look at it. The image is real, and the stars are real, and the rotation is real. But the stars are not enough. There are not enough of them, by mass, to keep the galaxy from flying apart. Andromeda spins too fast for the gravity its visible stars can supply. By every measurement we have ever made, it should be unwinding into the dark space around it, scattering its outer arms into intergalactic distances at hundreds of kilometers per second. It is not unwinding. It is not unwound for the past 10 billion years. Something else is holding it together. Something that does not shine, does not glow, does not absorb light, does not announce itself in any of the ways that matter in the universe has, until now, been expected to behave. This something accounts for roughly 85% of all the matter in the cosmos. By every cosmological measurement we have, by every count of galaxies and every map of cosmic structure, and every survey of the early universe, the matter that emits light, the matter we can see, the matter our entire scientific picture of the world has been built on, makes up only about 1/6 of what is actually out there. The other 5/6 is invisible. It surrounds galaxies in enormous spherical halos extending far beyond the stars. It fills the space between galaxy clusters. It threads the cosmos in vast filaments along which the visible universe is strung like beads on a string. It was present at the formation of the first galaxies. It is in every cubic meter of every place in the cosmos, and in every room and every body on this planet, including yours. In this video, we follow the long process by which the universe revealed that it was not what it seemed. The story is not one of sudden revelation. It is one of small inconsistencies that refuse to disappear, of careful measurements made over decades by people who suspected they had made errors, of theoretical proposals that turned out to be wrong, of experiments built in deep mines and at the South Pole and in orbit around the Earth, each of them designed to catch a glimpse of the substance that makes up most of the universe, and each of them so far finding nothing. The story is unfinished, but it is also one of the most precisely characterized mysteries in the history of science. We do not know what dark matter is, but we know an extraordinary amount about how it behaves. We know how much of it there is. We know where it gathers. We know what it does not do. We know it must exist, in some form, because the universe makes no sense without it. The question of what form is one of the open questions of our time, and one we will arrive at by the end. Begin, then, with the visible universe. For most of human history, this was the only universe anyone considered. The stars in the night sky, the planets, the moon, the sun. These were the matter of the cosmos. Telescopes extended the catalog, revealing fainter stars, then nebulae, then other galaxies, then galaxy clusters. By the early 20th century, the picture had grown enormously. The Milky Way was understood to be one galaxy among many, Other galaxies were observed to be moving apart from one another. And from this, Edwin Hubble inferred that the universe was expanding. The cosmos was vast, much vaster than anyone had previously imagined. But it appeared to be made of the kind of stuff that telescopes could see. Stars, gas, dust, light. This picture was beautiful and orderly. It was also wrong, although not in the way anyone expected. The stars and the gas and the dust are real. They behave as the laws of physics predict. There is nothing fictional about the visible universe. The problem is simpler and stranger. There is not enough of it, by an enormous margin, by a factor of more than 5. The visible matter, the matter built from atoms, the matter the periodic table catalogs, the matter that humans and planets and stars are made of, accounts for only about 15% of all the matter in the universe. The rest is something else. The first hint that this might be the case came in the early 1930s from an astronomer with a fierce temperament and a habit of being right too early. Fritz Zwicky was Swiss, working at the California Institute of Technology, and he had been studying a cluster of galaxies in the constellation Coma Berenices. The Coma cluster, as it is now called, contains about 1,000 galaxies, gravitationally bound to one another, drifting through space as a single enormous structure. Zwicky measured the speeds at which the individual galaxies were moving within the cluster. He found that they were moving very quickly. Some of them were moving at thousands of kilometers per second, fast enough that, by every law of gravitation that he knew, they should have been escaping the cluster entirely. The combined gravity of all the visible mass, all the stars in all the galaxies, was not nearly strong enough to keep them bound. The cluster, by every standard calculation, should have flown apart long ago. It had not flown apart. It was visibly there, in the sky, a coherent structure of 1,000 galaxies that had been drifting together for billions of years. Zwicky concluded that there must be more mass in the cluster than the visible galaxies could account for. He estimated that the missing mass exceeded the visible mass by a factor of several hundred. He called the unknown substance Dunkle Materie, which is the German term for dark matter, and he published his calculation in 1933. For the next 40 years, almost no one took the results seriously. The science of cosmology was young. Measurements of galaxy speeds were difficult, prone to error, and the techniques Zwicky had used were new. His personality also did not help. He was abrasive, dismissive of colleagues, and given to public denunciations of those who disagreed with him. He referred to fellow astronomers as spherical bastards, on the grounds that they were bastards however you looked at them. He was difficult to ignore, but he was also easy to dismiss, and the missing mass problem in the Coma cluster was filed away as an oddity. Perhaps the calculations were off. Perhaps the measurements were inaccurate. Perhaps there was some explanation involving hot gas, or rapidly moving objects we had not yet detected. The thought that the universe might contain a vast quantity of something we could not see was, at the time, not a thought anyone wanted to take seriously. Zwicky's result, however, did not go away. It just waited. Over the following decades, other observations would emerge from other astronomers, looking at other systems, finding the same pattern in different places. The galaxies in the Virgo cluster were moving too fast. The galaxies in the Hercules cluster were moving too fast. Wherever astronomers measured the dynamics of galaxy clusters with enough precision, the visible matter was insufficient to explain what was holding them together. Each observation, taken alone, could perhaps be doubted, but the pattern was becoming difficult to ignore. What turned the missing mass problem from an oddity into a crisis was not the dynamics of galaxy clusters. It was the dynamics of individual galaxies, observed by a woman who became one of the most important astronomers of the 20th century, working with an instrument that, at the time, was considered too modest for the question she was asking. Her name was Vera Rubin, and beginning in the late 1960s, she would gather the evidence that finally made dark matter impossible to dismiss. But before we reach Rubin, it is worth dwelling for a moment on what the universe looked like in the years before her work. Astronomers in the 1950s and 60s had a picture of galaxies that seemed coherent. A galaxy was a flat rotating disk, like a vast frisbee, with a dense bulge of stars at the center and spiral arms extending outward. The stars near the center orbited the galactic core quickly because the gravity of all the central stars pulled on them strongly. The stars in the outer arms, where there were fewer stars and less mass, orbited more slowly. This was simply Kepler's third law of planetary motion, applied on a galactic scale. In our own solar system, Mercury orbits the Sun once every 88 days, while distant Neptune takes 165 years to complete a single orbit. The outer planets move slowly because the gravitational pull from the Sun is weaker out there. Astronomers expected that galaxies would behave the same way. The visible mass of a galaxy is concentrated near its center. The stars in the outer regions should therefore orbit slowly, as if they were drifting at the periphery of a giant gravitational well whose floor lay near the galactic core. This was the picture in textbooks. It was the picture in the minds of astronomers when they looked at galaxies in the sky. And it was completely wrong. The stars at the outer edges of galaxies, hundreds of thousands of light years from their cores, were not moving slowly. They were moving at almost exactly the same speed as the stars in the middle. The rotation curves of galaxies, when plotted out, did not slope downward toward the edges as Kepler's law predicted. They were flat. The galaxies were rotating like solid bodies, with the outer regions sweeping around at hundreds of kilometers per second, exactly as fast as everything else. For the visible mass of a galaxy, this was impossible. The gravity supplied by the stars and gas could not hold the outer regions at that speed. They should have been flung off into intergalactic space. The fact that they were still there, still orbiting, still part of the galaxy after billions of years, meant that something else was supplying the gravity. Something invisible. Something that extended far beyond the visible disk of stars, surrounding each galaxy in a vast halo that contained most of the mass of the entire system. This is where Vera Rubin's work begins. And from this point onward, the universe stopped being what astronomers thought it was. Vera Rubin was born in 1928 in Philadelphia, the daughter of an electrical engineer who built her a telescope when she was a child. She watched the sky from her bedroom window, tracked the motions of stars, and decided early that she wanted to be an astronomer. The field at the time had almost no women in it. When she applied to graduate school at Princeton in the late 1940s, the astronomy department did not accept women, and would not for another 20 years. She went to Cornell instead, then to Georgetown for her doctorate, working with the cosmologist George Gamow on questions about the large-scale structure of the universe. She had 2 children before finishing her thesis. She defended it in 1954. In her early career, Rubin worked on a question that would not become fashionable for another 20 years, the large-scale motions of galaxies. In 1950, while still a graduate student, she presented a paper at the American Astronomical Society arguing that galaxies might not be moving uniformly with the expansion of the universe, but might be carrying out additional motions of their own, swirling on scales much larger than individual galaxies. The audience, mostly older male astronomers, was skeptical. Some were openly dismissive. The paper was not published in any leading journal. Rubin, then 22 years old and the mother of a small child, went home and resumed her work without complaint. Decades later, when the existence of large-scale galaxy flows was established beyond doubt, the early paper would be cited as one of the first hints that the universe was full of motion that simple expansion did not explain. At the time, no one had wanted to hear it. Rubin developed a quiet discipline of working on problems that seemed too modest, too slow, or too peripheral for the rest of the field. She measured things others ignored. She gathered data that others would not bother with. The pattern would serve her well when, 20 years later, she sat down to measure how Andromeda rotated. For the next 15 years, she worked on various problems in galactic dynamics, building a reputation as a careful and patient observer, the kind of astronomer who would spend hundreds of nights at a telescope to gather a single dataset. In the late 1960s, she began a collaboration with another astronomer, Kent Ford, who had developed a new kind of spectrograph, an instrument that could measure the speeds of objects in space by analyzing the light they emitted. The instrument was unusually sensitive. It could detect the slight shift in wavelength of light coming from stars moving toward or away from Earth, even when those stars were faint and far away. With Ford's spectrograph and the 4-meter telescope at Kitt Peak Observatory in Arizona, Rubin set out to do something that, on its face, sounded modest: measure how stars move within nearby galaxies. She began with Andromeda. It was the obvious choice. Andromeda is the closest large spiral galaxy to our own, large enough and bright enough that individual stars and gas clouds within it could be studied in detail. Rubin and Ford pointed the spectrograph at successive regions of the galaxy, working their way from the bright central bulge outward to the faint outer arms. At each position, they recorded the spectrum of light from the stars and gas in that region, and from the spectrum, they could calculate how fast that region was moving around the center of the galaxy. What they expected to see was what every textbook described: speeds rising as they moved outward from the center, peaking somewhere in the bright inner regions where most of the visible stars were concentrated, then falling away as they reached the dimmer outer disk. The rotation curve, plotted as a graph of speed against distance from the center, should look like a hill, climbing to a peak and then declining on the far side, exactly the shape the gravity of the visible matter would produce. That is not what they saw. The speeds climbed in the inner regions, as expected. But then, instead of declining, they stayed flat. Region after region, all the way out to the faint edges of the visible galaxy, the rotation speed remained essentially constant, around 220 kilometers per second. Each measurement took hours. The spectrograph had to be carefully aligned with a particular point in the galaxy. The light from that point, gathered by the telescope over a long exposure, had to be passed through the spectrograph and recorded on photographic plates, which were then developed and analyzed by hand. A single rotation curve, with measurements at perhaps 50 points across the face of a galaxy, could take many nights of observing to assemble. Rubin and Ford did this for galaxy after galaxy, year after year. The work was tedious. The conditions were often difficult. Telescope time at the major observatories was competitive, and Rubin, working on what most of the field considered a routine survey, often received less than ideal slots, observing on nights when the seeing was poor or the moon was bright. She would describe these nights years later with a kind of patient amusement: the cold of the dome, the smell of the photographic chemicals, the endless, careful work of pointing the telescope and waiting for the light. The graph did not show a hill. It showed a hill rising and then becoming a plateau, extending outward as far as Rubin's measurements could reach. The outer stars of Andromeda, hundreds of thousands of light years from the galactic center, were sweeping around as fast as the stars much closer in. Rubin checked her data. She and Ford repeated the measurements. They examined sources of error. They considered whether the spectrograph might be miscalibrated, whether the orientation of the galaxy on the sky might be distorting their readings, whether there might be some subtle effect of how light interacts with intervening dust. They tested everything they could think of. The result did not change. Andromeda's outer regions were moving at speeds that the visible mass of the galaxy could not possibly sustain. If this had been only Andromeda, the result might have been dismissed as a peculiarity. Perhaps Andromeda was unusual. Perhaps something about its history had given it a strange rotation pattern. So Rubin and Ford moved on to other galaxies. They observed Messier 81, a bright spiral in the constellation Ursa Major, flat rotation curve. They observed NGC 4258, a spiral with prominent jets, flat rotation curve. They observed NGC 7331, sometimes called the Milky Way's twin because of its similar size and shape, flat rotation curve. By the late 1970s, Rubin had measured the rotation curves of more than 60 galaxies. Every single one was flat in its outer regions. The pattern was universal. The implication was inescapable. Either Newton's and Einstein's theories of gravity were wrong, in a way they had never been wrong before in 2 centuries of testing, or there was a tremendous amount of unseen mass in every galaxy, distributed in a way that extended far beyond the visible stars. Most physicists, presented with this choice, found the second option more believable. Modifying gravity is a drastic step, and Newtonian gravity had been verified to extraordinary precision in the solar system, in laboratory experiments, in the motions of binary stars. In every context anyone had been able to test. To modify it on galactic scales, while leaving it intact on all smaller scales, would require a theory of remarkable subtlety. To postulate instead that galaxies contained some kind of invisible matter that did not interact with light, that was the more conservative choice. Strange, but conservative. By the early 1980s, the dark matter hypothesis had moved from the margins of cosmology into the mainstream. Astronomers began to model galaxies as consisting of 2 components: a visible disk of stars, gas, and dust, embedded inside a much larger, roughly spherical halo of dark matter. The halo was invisible, but its presence could be inferred from the way it shaped the motions of the visible material. The visible galaxy was, in this picture, only the bright center of a much larger structure. If you could see the dark matter halo of the Milky Way, it would appear as an enormous diffuse sphere extending hundreds of thousands of light years in every direction, with our familiar spiral disk embedded near the middle, like the bright yolk inside a vast pale egg. The mass of the dark matter halo in our galaxy and in nearly every other large galaxy that has been studied turns out to be about 10 times the mass of the visible matter. 10 times. For every kilogram of stars, gas, and planets in the Milky Way, there are about 10 kilograms of dark matter, spread out in the halo, gravitationally shaping the motion of everything else. The visible Milky Way, the great spiral arms, and the central bulge, and the disk of dust that we see edge on in the summer sky, is only about 1/10 of the actual galaxy. The rest is invisible. This is a strange fact to sit with. The thing we call the Milky Way, the structure that dominates the night sky on a clear evening, the spiral arms photographed by countless telescopes, the disk that contains the Sun and Earth and every star that has ever been named, is not even close to being the whole galaxy. It is the visible tip of something much larger. The actual extent of the Milky Way, including its dark matter halo, reaches roughly halfway to Andromeda. The Andromeda galaxy, 2.5 million light-years away, is approached by our halo from one side as its own halo extends out from the other. Some calculations suggest the 2 halos may already be in contact. Rubin's work was received initially with the kind of caution that scientific communities reserve for results that overturn existing pictures. Her papers were not dismissed, but they were not immediately celebrated either. Through the 1970s and 80s, other groups attempted to replicate her measurements, looking at different galaxies with different instruments. The results held. The rotation curves were flat. By the late 80s, the existence of dark matter halos around galaxies was widely accepted, although what the dark matter was made of remained completely unknown. Rubin herself was modest about her contribution. In interviews late in her life, she said she had not set out to discover anything earth-shaking. She had simply wanted to know how galaxies rotated. She had been curious about the dynamics, and the dynamics had told her something the universe had been keeping quiet for billions of years. She died in 2016 at the age of 88. She never received the Nobel Prize, which many in the astronomical community considered a serious oversight. Her name is attached to a new observatory in Chile, the Vera C. Rubin Observatory, which began operations in 2025, and which will, over the coming decade, map billions of galaxies and almost certainly produce the most detailed survey of dark matter ever undertaken. By the time Rubin's results were established, the dark matter problem had a clear shape. There was something in every galaxy, and apparently in every cluster of galaxies, that exerted gravity but did not emit light. It outweighed the visible matter by a factor of about 10 in galaxies, and by even more in clusters. It did not absorb light either. It did not glow in any frequency anyone had checked. It passed through itself, through stars, through planets, through everything, as if it were not there, interacting only through its gravity. This was an astonishing list of negatives. The challenge, from the late 70s onward, was to figure out what it was. The first guesses focused on familiar materials. What if the dark matter was made of ordinary matter, atoms and molecules, that simply happened to be in forms that did not produce much light? Could it be, for instance, very faint stars, smaller than the sun, so dim they could not be seen at the distances of galactic halos? Could it be brown dwarfs, objects too small to ignite as stars, drifting cold through space? Could it be black holes, formed from stars that had collapsed long ago, scattered through galactic halos and detectable only by their gravity? These categories were given a collective name, MACHOs, for massive compact halo objects. The acronym was deliberately playful, but the question was serious. If the dark matter was made of these kinds of ordinary, if dim, objects, then it was not so deeply mysterious. It was just ordinary stuff we had failed to catalog. To test this idea, astronomers used a technique called microlensing. According to general relativity, any massive object that passes in front of a distant star will briefly bend the star's light around itself, acting as a kind of natural lens and causing the star to appear momentarily brighter. The brightening lasts a few weeks to a few months and then fades. If the halo of the Milky Way contained large numbers of MACHOs, then surveys of millions of stars should occasionally catch one of these brightening events, as a passing MACHO bent the light of a background star. Several large surveys were undertaken in the 1990s to look for exactly this effect. They scanned millions of stars in the Large Magellanic Cloud, a nearby satellite galaxy of the Milky Way, watching for the telltale brightenings. The surveys did find microlensing events, but not enough of them. The number of brightenings observed was far below what would be expected if MACHOs made up a significant fraction of the dark matter halo. Whatever the dark matter was, it could not be primarily made of compact, ordinary objects. Faint stars, brown dwarfs, and stellar mass black holes simply were not numerous enough. The MACHO hypothesis had been tested and, for the most part, ruled out. Around the same time, an entirely different line of reasoning was pointing in a different direction. In the first few minutes after the Big Bang, when the universe was hot and dense enough for nuclear reactions to occur, hydrogen and helium were produced in specific ratios that depended on the amount of ordinary matter present. By measuring those ratios in the most ancient parts of the universe, astronomers could calculate how much ordinary matter, made of protons and neutrons, had been created in the early cosmos. The answer was clear and unambiguous. The total amount of ordinary matter, including stars, planets, gas, dust, and everything else made of atoms, was only about 15% of the total matter required to explain the gravitational behavior of galaxies and clusters. Even if every atom in the universe were somehow hidden in dark stars or black holes or cold gas clouds, the total mass would still fall far short of what the dark matter needed to be. This was a crucial result. It meant that dark matter could not be made of the kind of matter that humans, planets, and stars are made of. The dark matter was not just a population of dim, ordinary objects. It was something different. Something that was not made of protons and neutrons. Something that interacted with light not weakly, but essentially not at all. Something fundamentally new. The question of what that something might be is where the story moves next, into a particle physics that operates on scales unimaginably smaller than galaxies, but which may be where the answer ultimately lies. In 1977, just as Rubin's rotation curves were beginning to convince astronomers that dark matter must exist, three particle physicists at the University of Chicago published a paper that quietly reframed the whole problem. Their names were Benjamin Lee, Steven Weinberg, and a collaborator named Kim Griest. They were not astronomers. They were theorists who worked on the physics of fundamental particles, the kind of physics done in laboratories where particles are smashed together at enormous energies, and the debris is analyzed for clues about the basic structure of matter. They had been thinking about a particular kind of hypothetical particle, one predicted by extensions of the standard model of particle physics. The particle had a name, or rather an acronym. It was called a WIMP, for Weakly Interacting Massive Particle. The paper they published showed something interesting. If such a particle had existed in the early universe, in the first fractions of a second after the Big Bang, it would have been produced in enormous quantities, and it would have survived to the present day in roughly the amount needed to account for the dark matter. The coincidence was striking. The same particle physics that suggested the existence of WIMPs on entirely independent grounds also predicted the right amount of leftover material to be the dark matter. Physicists call this the WIMP miracle. Although the word miracle is used here in its technical sense, meaning a coincidence too neat to ignore. For the next 4 decades, the WIMP hypothesis would dominate dark matter research. The idea was elegant. A WIMP was, in this picture, a heavy particle, perhaps 100 times the mass of a proton, or 1,000 times, or 10,000 times. It would have been produced in the hot soup of the early universe, then cooled and slowed as the universe expanded, eventually settling into the diffuse halos surrounding galaxies. It would not interact with light because it carried no electromagnetic charge. It would not interact with the strong nuclear force that holds atomic nuclei together. It would interact occasionally and very faintly with ordinary matter through what physicists call the weak nuclear force, the same force that governs radioactive decay. This is where the WIMP gets its name. It interacts weakly. Not zero, but barely. Like a ghost that mostly passes through walls, but very rarely brushes against one of them. The hope, from the late 1970s onward, was that this faint interaction might be detectable. If WIMPs filled the halo of the Milky Way, and the Earth was moving through that halo as it orbited the Sun, then trillions of WIMPs must be passing through the planet every second. Most of them would pass straight through without interacting with anything. But very occasionally, a WIMP might collide with an atomic nucleus in some terrestrial detector, depositing a tiny amount of energy as it scattered. If you built a sensitive enough detector and shielded it from every other source of stray signals and waited long enough, you should eventually see those rare collisions. The signal would be small, but it would be unmistakable. It would be the first direct detection of dark matter, and it would, in a single moment, transform an inferred substance into a measured one. The first generation of dark matter detectors were built in the 1980s. They were small by modern standards, perhaps a kilogram of detector material in total, But the experiments were ambitious. They had to be placed deep underground, far below the surface of the Earth, to shield them from cosmic rays. Cosmic rays are charged particles, mostly protons, that constantly bombard the Earth from space. They produce signals in any detector built on the surface, and those signals would drown out the rare faint signals expected from WIMPs. To avoid them, the experiments were placed in old mines and tunnels, often more than a kilometer below ground. The Sudan mine in Minnesota, the Gran Sasso laboratory under a mountain in central Italy, the Stawell mine in Australia, the Bulby mine in Yorkshire, England. Each of these underground laboratories became home to detectors designed to catch the rare interactions of dark matter particles with ordinary matter. The early detectors were simple devices. A block of crystal, often germanium or silicon, cooled to extremely low temperatures, just above absolute zero. When a particle collided with one of the atoms in the crystal, the atom would recoil, depositing a small amount of energy in the form of heat and ionization. The detector measured both. If the ratio of heat to ionization was right, the signal might be a WIMP. If the ratio was wrong, it was almost certainly something else, a stray neutron or a passing electron from a radioactive decay somewhere in the surrounding rock. The experiments ran for years at a time, accumulating data, slowly improving their sensitivity. Through the 1990s and early 2000s, the detectors grew larger, more sensitive, and better shielded. They moved deeper underground. They were surrounded by elaborate systems of shielding designed to block every kind of stray signal. They became some of the quietest places in the world, in the technical sense that they were exposed to fewer background particles than anywhere else on Earth. The detectors did not, in this period, find dark matter. They set increasingly stringent limits on how often WIMPs could be interacting with ordinary matter, but they did not detect any actual interactions that could be confidently attributed to dark matter. Each new experiment improved on the last by a factor of 2 or 3 or 10. Each was capable of catching rarer and rarer signals, and each, after years of running, came up empty. The WIMP, if it existed, was even more weakly interacting than the early predictions had suggested. The miracle, if there was one, was hiding harder than expected. Through the 2000s and 2010s, the experiments grew larger still. The first generation of dark matter detectors had used perhaps a kilogram of detector material. The next generation used tens of kilograms. The generation after that used hundreds of kilograms. The current generation, in operation as this is being recorded, uses several tons. The detectors have become enormous, exquisite instruments, capable of catching interactions so rare that, if a WIMP exists at any energy that current theory suggests is plausible, the experiments should now be detecting it. The leading experiment of the current era is called LUX-ZEPLIN, located in the Sanford Underground Research Facility in South Dakota, more than 1.5 kilometers below the surface. It uses 7 tons of liquid xenon, cooled to about -100 degrees Celsius, surrounded by enormous tanks of ultra-pure water and additional layers of shielding. If a WIMP collides with a xenon nucleus in the detector, the collision produces a tiny flash of light and a tiny pulse of ionized electrons. Both are measured. The combination is analyzed for evidence of a dark matter signal. LUX-ZEPLIN has been running since 2023. As this video is being recorded in 2026, it has not yet detected dark matter. Neither has its competitor, Xenont, located in the Gran Sasso laboratory in Italy. Neither has Pandex in China. The combined sensitivity of these experiments is now extraordinary. They have ruled out vast regions of the theoretical parameter space in which WIMPs might exist. The most popular versions of the WIMP hypothesis, the ones that motivated the field for 4 decades, have now been pushed into ever narrower corners of the possible. Some physicists have begun to wonder whether the WIMP hypothesis is, in fact, wrong. whether the dark matter is not a WIMP at all. Whether the elegant coincidence of the WIMP miracle was just that, a coincidence, and the truth lies elsewhere. This is not yet a settled conclusion. There remains a region of parameter space, at lower interaction strengths and slightly different masses, where WIMPs could still exist and still escape detection. The next generation of detectors, scheduled for the late 2020s and early 2030s, will probe this remaining region. They will use tens of tons of detector material instead of tons. They will be more sensitive by another factor of 10 or 20. If WIMPs exist at any plausible mass and interaction strength, they should be detected. If they are not detected, the WIMP hypothesis will, at last, be effectively ruled out, and the field will have to look elsewhere. While the WIMP searches have continued, alternative ideas have grown in prominence. One of the leading alternatives is the axion, a particle proposed in 1977 for entirely different reasons. The axion was not originally invented to solve the dark matter problem. It was invented to explain a puzzling feature of the strong nuclear force, the force that binds protons and neutrons together inside atomic nuclei. The strong force, as far as anyone has been able to measure, treats matter and antimatter almost identically, which is a strange thing for a fundamental force to do. There is no obvious reason it should. The axion, if it exists, would explain this symmetry. The particle would be extremely light, far lighter than a WIMP, perhaps a billionth of the mass of an electron. It would interact with ordinary matter even more weakly than a WIMP, so weakly that direct detection through scattering experiments would be hopeless. But it would, in the conditions of the early universe, have been produced in enormous quantities, enough to account for all the dark matter in the cosmos. The axion hypothesis has the same elegance as the WIMP. It solves two problems at once, the strong force symmetry problem and the dark matter problem, with a single new particle. And like the WIMP, it can be searched for, although the search is technically very different. Axions, if they exist, can be converted into photons in the presence of a strong magnetic field. Detectors designed to look for axions use enormous superconducting magnets, cooled to near absolute zero, surrounding sensitive radio receivers that listen for the faint signal of axions being converted into photons of a specific frequency. The leading axion experiment, called ADMX, located at the University of Washington, has been running for years. So have several others with names like Haystack and Abracadabra. None of them has yet detected an axion, but they have steadily ruled out portions of the possible axion mass range. The search continues. A third class of candidates is more exotic. It includes sterile neutrinos, hypothetical particles related to the ordinary neutrinos of the Standard Model, but heavier and even more weakly interacting. It includes primordial black holes, formed not from the collapse of stars, but from density fluctuations in the very early universe, possibly small enough that they could constitute the dark matter halos of galaxies. It includes ideas from string theory and from extra dimensions, in which the dark matter might be a kind of particle that exists in higher dimensional spaces and interacts with ordinary matter only through gravity. Each of these candidates has its proponents, its experimental programs, and its own particular signatures. None has yet been detected. The dark matter problem, by the mid-2020s, has reached a curious moment. The evidence that dark matter exists is overwhelming and continues to grow. The motions of galaxies, the dynamics of galaxy clusters, the patterns of gravitational lensing, the temperatures of hot gas in clusters, the structure of the cosmic microwave background, the formation of large-scale structure in the universe. All of these point, with extraordinary consistency, to the existence of a vast amount of matter that does not interact with light. The total mass of this dark matter, the way it is distributed, the way it has evolved across cosmic history, are all known to remarkable precision. And yet, despite 40 years of experimental effort by hundreds of physicists in dozens of laboratories, no one has detected an actual particle of it. The substance that makes up most of the matter in the universe remains, at the level of individual particles, unobserved. This is one of the strangest situations in the history of physics. A new kind of matter, vastly more abundant than the ordinary kind, fully required by every cosmological observation, and yet so far refusing to be caught in any laboratory. The frustration in the field is real. So is the determination. There is something out there, and we are going to find it. The only question is when and what it turns out to be. There is, however, another possibility that some physicists have always taken seriously, and which has gained more attention in recent years. What if the dark matter does not exist? What if the apparent need for it is a sign that something else is wrong, not with the matter content of the universe, but with our understanding of gravity itself? The next part of the story is about that idea, and about why most physicists, despite serious effort, have not been able to make it work. The idea that gravity itself might need modifying, rather than positing a new kind of invisible matter, is at least as old as the dark matter problem. From the moment Zwicky's results appeared in 1933, some physicists wondered whether the missing mass might be a sign that the laws of gravitation, as Newton and Einstein had formulated them, simply broke down at very large scales. After all, gravity had been tested in detail only within the solar system and a few other accessible contexts. On the scales of galaxies and clusters, the theory was an extrapolation. Extrapolations sometimes fail. Perhaps the universe was telling us not that there was missing mass, but that gravity behaved differently when it was very weak. The most influential version of this idea was developed in the early 1980s by an Israeli physicist named Mordechai Milgram. Milgram was working at the Weizmann Institute when he noticed something striking about the rotation curves Rubin had been measuring. The flat outer regions of the curves seemed to set in at a particular acceleration. Wherever the gravitational acceleration on a star dropped below a certain very small value. Around 1/10 of the acceleration we feel from Earth's gravity at the surface, the star's motion stopped obeying Newton's laws in the usual way. Milgram proposed that this was not a sign of dark matter, but a sign that gravity itself was different in this regime. He formulated a modification of Newton's second law, the equation that relates force, mass, and acceleration, designed to take effect only at these extremely small accelerations. He called the proposal Modified Newtonian Dynamics, or MOND. MOND was an audacious idea. It said that there was no missing mass at all. The galaxies contained exactly what they appeared to contain. The reason the outer stars were not flying away was that gravity, at the very low accelerations relevant in galactic outskirts, was stronger than Newton's equations predicted. Milgram's modified law, with a single new constant fitted from observations, reproduced the flat rotation curves of every galaxy that had been measured. It also predicted, correctly, a number of relationships in galaxy data that the standard dark matter picture did not naturally explain, including a tight correlation between a galaxy's visible mass and the speed at which its outer regions rotate. This relationship, known as the baryonic Tully-Fisher relation, falls out of MOND essentially for free. From the dark matter perspective, it requires a more elaborate explanation. For decades, MOND remained a serious minority view. It had a small but dedicated group of advocates, mostly working at the boundary between astronomy and theoretical physics, who argued that the success of MOND in fitting galactic rotation curves was too striking to be a coincidence. They pointed out that MOND made specific predictions about new galaxies that had not yet been observed, and those predictions, when tested, often turned out to be correct. They argued that the dark matter community was being misled by the elegance of the WIMP hypothesis into ignoring observational evidence for a deeper modification of physics. The mainstream of the field, however, never embraced MOND. There were several reasons. One was that MOND, in its original form, was an empirical formula. It described how rotation curves behaved without explaining why. It modified Newton's second law in a way that had no obvious foundation in any deeper theory. Einstein's general relativity, the theory of gravity that supplanted Newton's, did not naturally accommodate MOND. To make MOND consistent with general relativity, which had been tested to extraordinary precision in the solar system and in other contexts, required elaborate theoretical constructions that struck most physicists as ugly and contrived. The relativistic versions of MOND that have been proposed, with names like TIVAs, are mathematically complicated and have not been universally accepted, even by MOND's supporters. But the more serious problem was that MOND, even with all its refinements, could not explain the dynamics of galaxy clusters. The original missing mass problem, the one Zwicky had identified in the 1930s, was about clusters, not about individual galaxies. In galaxy clusters, the discrepancy between visible mass and inferred mass is even larger than in galaxies. MOND, applied to clusters, can only reduce the discrepancy by a factor of 2 or 3. It cannot eliminate it. To make MOND fit cluster observations, its advocates have had to postulate the existence of, ironically, some kind of unseen matter inside the clusters. The very thing MOND was invented to avoid. Still, the strongest single argument against MOND, and in favor of dark matter, did not come from the dynamics of clusters in general. It came from a specific cluster, observed at a specific moment in its history, in which dark matter and visible matter happened to be physically separated from one another. The cluster is called the bullet cluster, although that name refers to one of its components rather than to the whole structure. It is located about 3.5 billion light-years from Earth in the constellation Carina. It is, in essence, the result of a collision between two galaxy clusters, in which one smaller cluster has passed through a larger one, producing a structure with two distinct components moving apart from each other. The cluster's catalog designation is 1E0657-558, but everyone calls it the bullet because of the appearance of the smaller component in X-ray images. The hot gas of the smaller cluster, plowed through the gas of the larger cluster, has formed a distinctive bow shock with a tapered shape, like a bullet emerging from a denser medium. The shock front is one of the cleanest examples of cluster-scale gas dynamics ever observed, and on its own, it tells a clear story about a violent collision. But the bullet-shaped gas is only one component of the system. There are also the galaxies in each cluster, distributed in a roughly diffuse way, far less dense than the gas. And there is the mass distribution, mapped by gravitational lensing, which does not coincide with either the galaxies or the gas in a simple way. The collision occurred about 150 million years ago in the frame of reference of the cluster, although the light from it has been traveling toward Earth for billions of years. The bullet cluster was first studied in detail in the mid-2000s. 3 different kinds of observations were combined. First, optical telescopes mapped the positions of the galaxies in each component, the ordinary visible stars and dust. Second, X-ray telescopes, particularly the Chandra X-ray Observatory orbiting Earth, mapped the positions of the hot gas, the diffuse glowing plasma that fills the space between galaxies in any cluster and which contains, by mass, far more material than the stars. Third, the technique of gravitational lensing was used to map the distribution of mass, all the mass, both visible and invisible. The gravitational lensing maps were made by observing how the light from galaxies behind the cluster was distorted as it passed through the cluster's gravitational field. The amount of distortion, point by point, revealed where the mass was. When the 3 maps were compared, a remarkable picture emerged. The galaxies, The stars and the gas were all where one might expect them to be after a collision between two clusters. But the gas, which made up most of the visible matter, had been stripped behind the centers of the two components. As the smaller cluster passed through the larger one, the gas of each cluster had interacted, friction had slowed it, and it had been left behind. The galaxies themselves, being much more sparsely distributed, had passed through one another without significant interaction, like two clouds of insects flying through each other in opposite directions. The gas had pooled in a region between the two clusters, glowing brightly in X-rays, where the friction of the collision had heated it to tens of millions of degrees. The gravitational lensing map, however, told a different story. The total mass, mapped by the lensing of background galaxies, did not coincide with the gas. It coincided with the galaxies. The two main peaks in the mass distribution were located not where most of the visible matter was, in the hot gas pool between the two clusters, but in the regions where the galaxies had ended up after the collision. The mass had moved with the galaxies, not with the gas. This was exactly what would be expected if the bulk of the matter in each cluster were a kind of dark matter that did not interact with ordinary matter except through gravity. The dark matter, in this picture, had passed through the collision essentially unimpeded, exactly as the galaxies had. The gas, made of ordinary matter and so subject to ordinary frictional forces, had been left behind. The pattern is so clean that it can be appreciated visually. If you look at a composite image of the bullet cluster, with the gas mapped in pink from X-ray observations, and the total mass mapped in blue from lensing, the two distributions are visibly separated. The pink gas sits in the middle, between the two main mass concentrations. The blue mass concentrations sit on either side, displaced from the gas by tens of millions of light years. The visible matter has been left behind by the collision. The invisible matter, the dark matter, has continued forward. There is no other interpretation of the image that makes physical sense. Whatever supplies the gravity in this cluster, whatever bends the light of the background galaxies, it is not the gas, and it is not the galaxies themselves. It is something else, distributed roughly with the galaxies but containing far more mass than they do, and behaving in a collision exactly as a non-interacting substance should behave. For modified gravity theories like MUND, the bullet cluster was a serious problem. In MUND, the gravitational field of a cluster should follow the distribution of visible matter, because there is no other matter to follow. The lensing map should peak where the gas peaks, since the gas contains most of the cluster's visible mass. The fact that the lensing peaks were displaced from the gas peaks meant that, whatever was causing the lensing, it was not the visible matter. Something else was there, something with mass but no luminous emission that had moved separately from the gas. The bullet cluster, in the years after its detailed observation, became known as a kind of smoking gun for dark matter. It showed, in a single well-studied system, that the dark matter could be physically separated from the visible matter. That was hard to reconcile with any modified gravity theory, in which gravity simply tracks ordinary mass. Since the bullet cluster, several other colliding clusters have been observed with similar techniques, and they have shown similar separations between mass and gas. The clusters MACSJ 002, 5.4-1222, the train wreck cluster, and several others all show the same pattern. Dark matter and gas separated. Modified gravity theories have not been able to account for these observations without invoking some kind of additional unseen matter, which defeats the purpose. The bullet cluster and its kin have not killed MOND entirely, but they have pushed it firmly to the margins of the field. Most physicists who work on the dark matter problem now consider the existence of dark matter, as some kind of substance distinct from ordinary matter, to be effectively settled. The remaining question is what that substance is. There is one more important kind of evidence for dark matter that has not yet been mentioned, and which closes the loop on the case. It is the cosmic microwave background, the faint glow of radiation left over from the early universe, which fills the entire sky and which has been mapped in extraordinary detail by satellites over the past 3 decades. The cosmic microwave background carries an imprint of the conditions of the universe when it was only 380,000 years old, when the first atoms were forming and the universe was becoming transparent to light. Tiny variations in the temperature of this background radiation, measured to a precision of 1 part in 100,000, encode information about every form of matter and energy in the early universe. By analyzing the statistics of these temperature variations, cosmologists can determine, with great precision, the total amount of ordinary matter, the total amount of dark matter, and the total amount of a third component called dark energy that drives the expansion of the universe. The numbers that come out are unambiguous. About 5% of the universe is ordinary matter. About 27% is dark matter. About 68% is dark energy. The dark matter component is roughly 6 times larger than the ordinary matter component, exactly as the galaxy and cluster observations had been suggesting for decades. The acoustic peaks in the cosmic microwave background, the specific patterns of hot and cold spots at different angular scales, encode information about the early universe in a way that has been compared to reading the score of a symphony played 13 billion years ago. The sound waves that propagated through the early plasma left their fingerprints in the temperature variations, and the precise pattern depends on how much ordinary matter, how much dark matter, and how much radiation were present at the time. Cosmologists have measured these patterns to extraordinary precision, first with the COBE satellite in the early 1990s, then with the WMAP satellite in the 2000s, and finally with the Planck satellite, which produced the definitive map between 2009 and 2013. The Planck data, combined with measurements from ground-based telescopes that have continued the work in higher resolution, give the most precise inventory of the universe's contents ever assembled. Dark matter is not an inference from indirect arguments. It is a measured component of the universe, as solidly established as the existence of hydrogen or helium. The cosmic microwave background is, in a sense, the most precise single measurement of how much dark matter the universe contains, and it provides a kind of independent check on every other line of evidence. The dark matter implied by rotation curves agrees, to within the uncertainties, with the dark matter implied by cluster dynamics, which agrees with the dark matter implied by gravitational lensing, which agrees with the dark matter implied by the cosmic microwave background. 4 very different kinds of observation, all pointing at the same total. The case for dark matter, as a real and abundant substance in the universe, is no longer seriously in question. The case for what it is, however, remains as open as it was 40 years ago. In the next stretch of this video, we move from the question of how much dark matter there is to the question of how it shapes the universe. Because dark matter is not just there. It does things. It built the cosmos as we know it. Without it, the universe we live in would not have formed. To understand what dark matter does in the universe, we have to go back to the beginning. Not to the beginning of dark matter as an idea, but to the beginning of everything, the first fraction of a second after the Big Bang, when the universe was a hot, dense, uniform soup of energy and particles. At that moment, the universe was almost perfectly smooth. The matter in it was distributed evenly, in every direction, to a precision of about 1 part in 100,000. There were no galaxies. There were no stars. There were no clouds of gas or planets or living creatures. There was only a homogeneous bath of radiation and particles, expanding and cooling, the same in every direction. And yet, here we are. The universe we live in is the opposite of uniform. It contains galaxies clustered into groups, groups assembled into clusters, clusters strung along filaments, filaments arranged into a vast cosmic web with enormous voids between them, regions hundreds of millions of light years across in which there is almost nothing, The transition from the smooth early universe to the lumpy modern universe is one of the most important processes in cosmic history. It is the process by which structure came into being, and dark matter is the central character in it. Imagine the universe as it was, almost perfectly smooth but not quite. The tiny departures from uniformity, the 1 part in 100,000 variations, were the seeds of everything that would later form. In regions slightly denser than average, gravity would pull additional matter inward, increasing the density further. In regions slightly less dense than average, matter would flow away, leaving the regions emptier still. Over time, the denser regions would grow denser, and the emptier regions would grow emptier. Structure would emerge from smoothness through gravitational amplification, the rich growing richer until the universe became a network of dense pockets separated by vast empty spaces. This process, called gravitational instability, was first worked out in detail by the Russian physicist Yakov Zeldovich and his collaborators in the 1970s, and it works, in broad outline, exactly as described. But there is a problem with the picture if you try to apply it only to ordinary matter. Ordinary matter, before the cosmic microwave background was released, was tightly coupled to radiation. It interacted constantly with photons, and the pressure of all those photons prevented it from collapsing under gravity. As long as the universe was filled with hot radiation, ordinary matter could not begin to clump. It oscillated, but it could not collapse. The clumping could only begin 380,000 years after the Big Bang, when the universe cooled enough for atoms to form and radiation to decouple from matter. 380,000 years is a long time on a human scale, but on a cosmic scale it is very short. From that moment until today, about 13.5 billion years have passed. During that time, ordinary matter had to clump into stars. Stars had to gather into galaxies. Galaxies had to assemble into clusters, and clusters had to weave themselves into the cosmic web. The calculation has been done. The amount of clumping that could be achieved by ordinary matter alone, starting from the small initial fluctuations and given the time available, falls far short of what we actually see. The galaxies should not yet exist. The cosmic web should still be smoothing itself out. The universe should look, even today, like a featureless fog of gas. Dark matter changes this. Because dark matter does not interact with photons, it does not feel the radiation pressure that suppresses ordinary matter in the early universe. From very early on, far earlier than the 380,000 year mark, dark matter could already begin to clump under gravity. While ordinary matter was still being pushed around by photons, dark matter was quietly assembling itself into dense regions. By the time ordinary matter was finally free to collapse, the dark matter had already done the preparation. There were dense pockets of it, preformed gravitational wells, waiting. The ordinary matter, when it was released from the photons, simply fell into the wells the dark matter had already built. Within a few 100 million years, the first stars and galaxies formed inside the dark matter halos that had been waiting for them. This is the central reason cosmologists believe dark matter must exist. Without it, galaxies would not have had time to form. The universe we live in would still be a uniform fog. Dark matter in this picture is not just a substance that exists alongside ordinary matter. It is the scaffolding on which the visible universe was built. Every galaxy formed inside a pre-existing dark matter halo. Every cluster of galaxies formed inside a pre-existing dark matter cluster. The visible universe is, in a sense, the bright decoration on a much vaster invisible architecture that was put in place long before any star ever shone. The detailed predictions of this picture have been tested extensively. Computer simulations run on the world's largest supercomputers can model the evolution of dark matter from the early universe to the present day. The simulations begin with the tiny fluctuations measured in the cosmic microwave background and follow them forward in time under the influence of gravity. They produce, after billions of simulated years, a universe that looks remarkably like the real one. Galaxies and clusters appear in the right numbers, in the right places, with the right sizes. The cosmic web of filaments and voids emerges naturally. The largest simulations to date, projects with names like the Millennium Simulation, the Illustris Simulation, and the more recent Flamingo and Millennium TNG simulations, model billions of galaxies across cubic regions, hundreds of millions of light-years across. The comparison with observations is striking. The simulated universe and the real universe look like the same place. The cosmic web itself is one of the most beautiful structures in nature. Galaxies, in the real universe, are not scattered randomly through space. They are concentrated along thin filaments, like beads strung on threads, with the threads woven into a vast three-dimensional network. Between the filaments are immense empty regions called voids, some of them stretching hundreds of millions of light-years across. The Bode's void, one of the largest empty regions known, is about 300 million light-years across and contains almost no galaxies at all. Around the voids and along the filaments, galaxies cluster in groups, then in clusters, then in superclusters, the largest gravitationally bound structures in the universe. Our own Milky Way is part of the local group, a small association of galaxies, including Andromeda and a few dozen smaller ones. The local group sits on the outskirts of the Virgo supercluster, which in turn forms part of a larger structure called Laniakea, a vast complex of superclusters about 500 million light-years across, defined in 2014 by the astronomer Brent Tully. Laniakea is so large that the gravitational pull of its center is detectable in the motions of galaxies hundreds of millions of light-years away, including our own. Within this vast structure, our position is unremarkable. The local group sits on the outer edge of the Virgo supercluster, far from any particular center, embedded in one of the strands of the cosmic web rather than at a major intersection. The Milky Way and Andromeda, the two large galaxies of the local group, are slowly approaching each other. Andromeda is moving toward us at about 110 kilometers per second, and in roughly 4.5 billion years, the two galaxies will collide and merge into a single larger galaxy. The collision will not be sudden, and individual stars within each galaxy will rarely come close to other stars. But the gravitational rearrangement will be profound. The combined dark matter halo of the merged system will eventually settle into a single roughly spherical structure, and the merged galaxy, sometimes called Milkomeda, will be the new gravitational anchor of the local group. The merger is, in a sense, already beginning. The dark matter halos of the two galaxies have already approached close enough that they are starting to perturb one another. The visible parts of the galaxies have a long way to go before they touch, but the invisible parts have already, in some sense, begun to interact. All of this structure, from the smallest galaxy to the largest supercluster, exists because dark matter built it. The filaments of the cosmic web are filaments of dark matter, with ordinary matter and galaxies strung along them. The voids are voids of dark matter, with very little ordinary matter inside them either. The clusters are dark matter clusters, with bright galaxies marking the densest regions. If you could somehow see the dark matter directly, the universe would look like a vast lacework, threads and knots and empty pockets. The visible galaxies just the brightest points along the framework. There is no way to see the dark matter directly, but there is a way to map it. Gravitational lensing, the same technique used on the bullet cluster, can be applied across the entire sky. Light from distant galaxies, passing through the intervening universe, is bent by every mass it encounters. The cumulative bending, statistically analyzed across millions of background galaxies, reveals the distribution of mass along the line of sight. This is called weak gravitational lensing, and over the past 2 decades, it has produced increasingly detailed maps of the dark matter distribution in the universe. The maps look, predictably, like the cosmic web. They show the same filaments and voids and clusters as the visible universe, but with extra structure that the visible matter alone does not display. The dark matter web is real, mappable, and consistent with the picture cosmologists had derived from theory. The Vera C. Rubin Observatory, which began full operations in 2025, is expected to produce the most detailed weak lensing maps ever made. Its survey, called the Legacy Survey of Space and Time, will photograph the entire southern sky every few nights for 10 years, accumulating images of billions of galaxies. From the statistical distortions of those galaxies, cosmologists will produce a 3-dimensional map of the dark matter distribution in our cosmic neighborhood, more precise than anything previously available. The dark matter, although still untouched and unidentified at the particle level, will be charted across the cosmos with a precision that exceeds the precision with which we know the shape of our own continents. This is the strange irony of dark matter research. On the largest scales, we know it well. We know how much there is. We know how it is distributed. We know how it has evolved across cosmic history. We can map its presence, predict its behavior, and use it to explain the structure of the visible universe. On the smallest scales, the scale of individual particles, we have no idea what it is. The substance is mapped and modeled and understood at the scale of galaxies, while remaining completely unknown at the scale of atoms. There is no other substance in the history of science about which we know so much and so little at the same time. Within galaxies, the dark matter forms enormous halos extending far beyond the visible disk. The halo of the Milky Way, our best studied example, is roughly spherical, with a radius of perhaps 300,000 light-years. The visible disk of stars is only about 100,000 light-years across. The halo extends 3 times as far in every direction and contains about 10 times more mass than all the visible stars and gas combined. We are, in a literal sense, embedded in a vast cloud of dark matter that surrounds our galaxy on all sides. The Sun moves through this cloud at about 220 kilometers per second as it orbits the galactic center. So does the Earth. So does every reader of this video, although no one feels the wind of dark matter on their skin. The halo is not perfectly smooth. It has structure of its own. Embedded within it are smaller clumps of dark matter, called subhalos, which are the gravitational remnants of smaller systems that the Milky Way absorbed over its history. Some of these subhalos contain dwarf galaxies, faint collections of stars whose visible matter sits inside a much larger envelope of dark matter. The Milky Way has about 60 known dwarf galaxy companions, ranging from the large Magellanic Cloud, easily visible in the southern sky, to faint objects like the Bode's dwarf or the Segway 1 dwarf, containing only a few thousand stars, but inferred to contain 1,000 times more dark matter. These small companions are some of the most dark matter-dominated systems in the universe. The dwarf galaxies that orbit the Milky Way are particularly illuminating because their dark matter content is so much larger than their visible content. In a normal galaxy, dark matter outweighs visible matter by a factor of about 10. In the faintest dwarf galaxies, the ratio is more like 1,000. These objects, sometimes called ultra-faint dwarfs, may contain only a few hundred or a few thousand stars, but they sit inside dark matter halos, large enough that the gravitational binding is dominated almost entirely by the invisible component. The stars in such a dwarf galaxy serve essentially as luminous tracers of a dark matter structure that contains them. By measuring the speeds of the few visible stars, astronomers can map the gravitational well in which they sit, and the gravitational well is entirely shaped by dark matter. Studying these objects is, in a sense, the closest astronomers can come to studying dark matter directly. The visible component is so faint that it almost does not interfere with the picture. What remains is a dark matter halo, lit by a sprinkling of stars, whose dynamics reveal the structure of the dark substance in unusually clean detail. They are, in a sense, almost pure dark matter, with only a sprinkling of visible stars to mark their presence. Surveys with telescopes like the Dark Energy Survey and the European Space Agency's Gaia mission have, over the past decade, revealed the structure of the Milky Way's halo in unprecedented detail. They have found long streams of stars wrapping around the galaxy, the visible debris of dwarf galaxies that were torn apart and absorbed billions of years ago. They have found gaps and substructures in those streams, which are interpreted as the gravitational fingerprints of invisible clumps of dark matter passing through. The Milky Way's halo, far from being a featureless cloud, is alive with structure, full of the ghosts of past collisions, and possibly threaded with substructures that the dark matter has built on its own. In the next stretch of this video, we turn to one of the deepest questions in the field. What if the dark matter is not just a substance that interacts only through gravity? What if it has structure of its own? What if there is a whole dark sector of physics, with its own particles and forces, hidden alongside the universe we know? For most of the history of dark matter research, the simplest picture has been the dominant one. Dark matter in this picture is a single kind of particle, interacting with ordinary matter only through gravity, and with itself in no significant way except through gravity either. It is, in effect, a cosmic dust of weakly interacting objects, scattered through the universe in vast halos, doing nothing but feel and exert gravitational pull. This picture has worked extraordinarily well on the largest scales. The structure of the cosmic web, the formation of galaxies, the dynamics of clusters, the patterns of the cosmic microwave background, all of these can be explained by assuming dark matter is a passive substance whose only role is gravitational. But in recent years, on smaller scales, this picture has begun to show cracks. Not large cracks. The simple model still works very well in most contexts. But careful observations of the inner regions of galaxies and of the small satellite galaxies that orbit larger ones like the Milky Way have turned up discrepancies between what the simulations predict and what the universe actually contains. Cosmologists have given these discrepancies names: the missing satellites problem, the core cusp problem, the too big to fail problem. Each of them refers to a specific way in which the simplest dark matter model seems to overpredict structure in the inner regions of galaxies. The differences are not enormous, and they may yet be explained by improvements in the simulations or by subtle effects involving the visible matter. But they have raised an intriguing possibility. What if the dark matter is not as simple as we have been assuming? What if it does more than just feel gravity? This is the idea behind self-interacting dark matter. In this picture, dark matter particles interact with one another through some force other than gravity, a force that operates only within the dark sector and has no significant effect on ordinary matter. The interaction would be too weak to detect in laboratory experiments, but strong enough, on cosmic scales, to alter the inner structure of dark matter halos. Dark matter particles in the dense centers of halos would occasionally scatter off one another, exchange energy, and redistribute themselves. The result would be a smoother, more uniform center to each halo, rather than the sharp central peak that the simplest models predict. Some observations of galaxy interiors are consistent with this kind of smoothing. Whether the smoothing is due to self-interacting dark matter or to ordinary matter feedback such as supernova explosions that stir up the centers of galaxies remains an open question. But the idea has opened a door that for a long time was closed. If dark matter can interact with itself, then it might have a far richer structure than physicists have traditionally assumed. There might not be just one kind of dark matter particle, but several. There might be a dark sector containing multiple species of particles, interacting through multiple forces, perhaps even forming complex structures the way ordinary matter does. There might be dark atoms made of dark protons and dark electrons, bound together by dark electromagnetic forces. There might be dark molecules, there might be dark stars or dark planets, or in the most speculative versions, dark life. These ideas are not, at present, supported by direct evidence. They are theoretical possibilities, allowed by what we know about the dark sector, but not required by it. They sit in the realm of plausible speculation rather than established science. There is, however, one thing the universe seems to be telling us about the dark sector, which is that it is unlikely to be very rich. If dark matter interactions were too strong, the dark matter would dissipate energy efficiently, the way ordinary matter does when it cools and collapses into stars and disks. The dark matter halos of galaxies would be flat, rotating disks rather than diffuse spheres. They are not. They are diffuse spheres. This suggests that whatever interactions exist in the dark sector, they are weak enough that the dark matter cannot cool and condense into smaller structures. The halos remain extended. They do not concentrate into dark disks or dark stars. The dark sector, whatever its internal complexity, behaves on large scales as if it were nearly collisionless. This does not mean self-interactions are absent. It means they are limited. The dark matter, on average, can scatter off itself at most, about once per particle over the age of the universe. That is a very low rate, but it is not zero. And even at this low rate, the effects on galaxy interiors can be significant. The next generation of telescopes and surveys, including the Rubin Observatory and the proposed square-kilometer array radio telescope, will produce observations precise enough to test self-interacting dark matter models against the simple collisionless picture. Within the next decade, we should know whether the dark matter interacts with itself at all, and if so, how strongly. There is another, even more speculative possibility. What if the dark matter is not a particle at all? What if it is something else entirely, a fluid, a field, a kind of geometric distortion of space-time? One class of such ideas treats dark matter as an extremely light field, much lighter than any particle that could exist in the standard picture. The axion, mentioned earlier, is the lightest of the standard dark matter candidates, with a mass perhaps a billionth of an electron's mass. But there are theoretical models in which the dark matter is even lighter by many more orders of magnitude. In these models, the dark matter behaves not like a collection of discrete particles, but like a continuous wave. Its wavelength would be enormous, comparable to the size of a galaxy. In the very lightest versions, called fuzzy dark matter, the wavelength of a single dark matter particle would be thousands of light years long. The dark matter halo of a galaxy would not consist of countless tiny particles drifting through space, but of a single enormous wave function, smooth on the scale of galaxies and rippled with structure on smaller scales. Fuzzy dark matter has interesting properties. It would naturally avoid the formation of very small structures, because the wave nature of the field smooths out fluctuations below a certain size. It might, in this way, explain the apparent absence of very small dark matter clumps that the simplest particle models predict. It would also produce distinctive patterns of interference and oscillation inside galaxies, patterns that might, in principle, be detectable in the motions of stars or in the distortion of background galaxy images. Several research groups are currently testing fuzzy dark matter against the observed structure of dwarf galaxies, where its effects would be most pronounced. The fuzziest end of the dark matter spectrum sits near the boundary between dark matter and dark energy. Dark energy, the other great mystery of modern cosmology, is the unknown component that makes up about 68% of the total energy budget of the universe, and which is driving the expansion of space to accelerate. Dark matter and dark energy are very different things. Dark matter clumps under gravity and forms galaxies. Dark energy is smooth and resistant to clumping, and pushes the universe apart rather than pulling it together. The two are not, as far as we know, related. But in some theoretical frameworks, the boundary between them blurs, and the dark sector becomes a single complicated structure with multiple components. Whether or not these unified pictures are correct, the existence of two separate unknown components, jointly accounting for 95% of the universe, is one of the largest indications that our current understanding of physics is incomplete. While theorists explore these possibilities, experimentalists continue the search. The direct detection programs for WIMPs and axions, described earlier, are part of a much wider experimental effort. There are also indirect detection programs, which look not for dark matter particles colliding with ordinary matter, but for the products of dark matter particles annihilating with one another somewhere in space. If dark matter particles can annihilate, they would do so most often in the densest regions of dark matter halos, the centers of galaxies, the centers of galaxy clusters, the cores of the dwarf galaxy companions of the Milky Way. The annihilations would produce a faint glow of ordinary particles, photons, electrons, and positrons, neutrinos, which would emerge from the dense regions and be potentially detectable on Earth. The Fermi Gamma Ray Space Telescope, launched in 2008 and still operating, has been searching for exactly this signal for nearly 2 decades. It maps the gamma ray sky and looks for excess emission from regions where dark matter should be densest. In 2009, a research group reported an apparent excess of gamma rays coming from the center of the Milky Way, a signal that some interpreted as the long-sought signature of dark matter annihilation. The interpretation was controversial. The galactic center is a crowded place, full of pulsars, neutron stars, and other potential sources of gamma rays, and disentangling a dark matter signal from these confounders is enormously difficult. Years of further analysis have not resolved the question. The signal might be dark matter. It might be a population of unresolved pulsars. The community is divided. New observations and more refined modeling continue. Other experiments have looked for indirect signatures of dark matter in different ways. The IceCube Neutrino Observatory, buried in the ice at the South Pole, looks for high-energy neutrinos that might come from dark matter annihilation in the Sun's core. The Alpha Magnetic Spectrometer, mounted on the International Space Station, measures the flux of cosmic ray particles, looking for excesses that might come from dark matter annihilation in the Milky Way halo. The Cherenkov Telescope Array, currently under construction in the Canary Islands and in Chile, will look for very high-energy gamma rays from dark matter annihilation in dwarf galaxies. Each of these experiments is sensitive to a different range of possible dark matter masses and interaction strengths, and together they cover an enormous swath of theoretical possibilities. Together, they have set strong limits on dark matter annihilation rates across many possible models. Like the direct detection experiments, they have so far seen no unambiguous signal. A third experimental approach is to try to create dark matter in the laboratory. If dark matter particles can be produced in nature, then they should also be producible in particle accelerators, where energies comparable to those of the early universe can be reached for brief moments. The Large Hadron Collider at CERN near Geneva has been running since 2010, smashing protons together at energies higher than any previous accelerator. The collisions produce showers of particles, most of which are detected and identified by enormous instruments surrounding the collision points. If a dark matter particle were produced in one of these collisions, it would escape the detector without leaving any trace, since it does not interact with ordinary matter. The signature would be missing momentum, a collision in which the total momentum of the detected particles is less than the momentum of the protons that went in. The missing momentum would be carried away by undetected dark matter. The challenge of the LHC searches is that Even if dark matter is being produced in collisions, the rate would be extremely low and the signal would be entirely indirect. A WIMP, if it appeared in a collision, would leave the detector without depositing any energy. The signature would be a kind of imbalance, a collision in which the detected particles add up to less momentum or energy than the protons that produce them. Such missing momentum events do occur in the data, but most of them are caused by ordinary neutrinos, which also escape detection. To identify a possible dark matter signal, the experimentalists must measure the rate of such events with extreme precision and compare them to predictions for known sources. So far, no excess above the expected background has been seen. The most stringent searches have looked specifically for the production of WIMPs alongside other detectable particles, the simplest configuration in which a dark matter signal could appear. The absence of such signals constrains the possible interaction strengths of WIMPs with ordinary matter, complementing the constraints from the underground experiments and approaching them from a completely different direction. The LHC has not yet seen any convincing signal of this kind. It has set limits on the possible masses and interaction strengths of WIMPs that complement the limits from underground experiments. Together, the direct detection experiments and the LHC searches have eliminated most of the parameter space in which the simplest WIMP models would have been expected to live. The WIMP, the central candidate of the first 40 years of dark matter research, is now in a difficult position. Not ruled out, but cornered and increasingly unlikely. If WIMPs do not turn out to be the answer, the next decade will be a critical one for the field. The remaining theoretical possibilities, axions, sterile neutrinos, fuzzy dark matter, self-interacting dark matter, will be probed by the next generation of experiments and observations. Some of those candidates will be ruled out. Some may be detected. The field is, in a sense, entering the phase where the easy possibilities have been exhausted, and the difficult ones must be confronted directly. In the next stretch of this video, we turn to one of the most personal and physical aspects of the dark matter problem. The dark matter is not somewhere far away, it is here. It is moving through us at this moment. And the way it moves through us has consequences, both for the search to detect it and for the strange physical reality of inhabiting a planet that drifts through a sea of unknown particles. The dark matter halo of the Milky Way is, by our best estimates, fairly smooth in the region around the Sun. Its density here is about 0.5 billionth of a gram per cubic centimeter. In more comprehensible terms, this works out to roughly 1/3 of a proton's mass per cubic centimeter, or about 0.5 kilogram of dark matter spread evenly through a volume the size of the Earth. Compared to the density of ordinary matter on a planetary surface, this is almost nothing. But on cosmic scales it adds up, and the total mass of dark matter in the Milky Way's halo is about 10 times the mass of all the stars and gas in the galaxy combined. The Sun moves through this halo as it orbits the center of the galaxy, sweeping at about 220 kilometers per second through the dark matter cloud that surrounds us. From the Sun's point of view, the halo is not stationary. It feels like wind, a continuous stream of dark matter particles flowing past us from the direction the Sun is heading, which happens to be roughly toward the constellation Cygnus. If you point at Cygnus on a summer evening, you are pointing into the headwind of the dark matter as it streams past the solar system. The wind speed, 220 kilometers per second, is far faster than any wind in any atmosphere. It is faster than the orbital speed of the Earth around the Sun, faster than the escape velocity from any planet, faster than anything we encounter in daily life. And yet we feel nothing. The dark matter blows through us, through the atmosphere, through the rock beneath our feet, through the Earth's core and out the other side, without leaving a trace. The Earth, in its yearly orbit around the Sun, adds its own motion to this picture. In June, the Earth's orbital velocity is in roughly the same direction as the Sun's motion through the galaxy. The two velocities add together and the dark matter wind from the Earth's point of view is slightly faster. In December, the Earth is moving in the opposite direction along its orbit, and its velocity partly cancels the Sun's motion. The dark matter wind in December is slightly slower. The difference is small, about 30 kilometers per second out of 220, but it is real and it is potentially detectable. If a dark matter direct detection experiment is sensitive enough, it should see a slightly higher rate of dark matter interactions in June than in December. This seasonal modulation, as it is called, is one of the cleanest possible signatures of dark matter, because no other physical process is expected to produce exactly the same pattern. The seasonal modulation has, in fact, been claimed by one experiment, and the claim has been controversial for decades. The experiment is called DAMA, located in the Gran Sasso laboratory in Italy. Since the late 1990s, DAMA has been operating an array of sodium iodide crystal detectors, looking for the small signals expected from dark matter particles scattering off the atomic nuclei in the crystals. From very early in its operation, DAMA reported a clear seasonal variation in the signal rate, with a maximum in early June and a minimum in early December, exactly as predicted for a dark matter wind. The amplitude of the variation is about a few percent, and the statistical significance, after more than 2 decades of data, is enormous. By its own internal measures, DAMA has detected dark matter. The problem is that no other experiment has been able to confirm this result. Other detectors, using different materials and different techniques, have searched for the same modulation. They have not found it. The parameter space in which DAMA's signal could correspond to a real dark matter interaction has been thoroughly excluded by experiments like Xenon T, Lux Zeppelin, and Pandax. Either DAMA is detecting a real signal that, for some reason, the other experiments cannot reproduce, or DAMA's modulation is caused by some unrecognized systematic effect, perhaps related to the seasonal variations in temperature, radon levels, or cosmic ray flux at the Gran Sasso laboratory. The community has been trying for years to resolve the discrepancy. Several new experiments have been built specifically to replicate DAMA's setup with different detector materials in different locations in order to test whether the modulation is real. The first results from these experiments, from the cosine 100 detector in South Korea and the Anais 112 detector in Spain, have begun to appear in recent years. They have not yet confirmed DAMA's signal, but the data are still being analyzed and the question is not yet settled. The DAMA controversy is one of the most peculiar standoffs in modern physics. An experiment with a clear, strong signal, persisting for more than 2 decades, claiming the discovery of dark matter, while every other experiment in the field disagrees. Most physicists, faced with this situation, conclude that DAMA must be wrong, and that the source of its signal is some terrestrial effect that has not yet been identified. But DAMA has been running for so long, and its result is so robust by internal measures that it cannot simply be dismissed. The resolution of this question, when it comes, will be one of the more important developments of the next few years. While the DAMA situation plays out, the broader picture of dark matter as a local phenomenon has been growing in detail. The dark matter wind through the solar system is not, on close inspection, perfectly smooth. The Milky Way halo, as discussed earlier, has structure. There are streams of dark matter flowing through the galaxy that originate in past mergers and in the gradual disruption of smaller systems by the Milky Way's gravity. Some of these streams pass through the solar system. The most famous of them is the Sagittarius stream, a long ribbon of stars and dark matter wrapping around the Milky Way several times, the remnant of the Sagittarius dwarf galaxy that is being slowly torn apart by the Milky Way's gravity. The Sagittarius stream passes within a few hundred light-years of the Sun, and its dark matter component, although not separately detectable, is part of the local dark matter density. Other streams have been identified through the motions of nearby stars, which trace the gravitational fingerprints of the underlying dark matter. The Gaia spacecraft, operating since 2013, has measured the positions and velocities of more than 1 billion stars in the Milky Way, and the analysis of these measurements has revealed dozens of stellar streams, each of them associated with a particular history of accretion. The dark matter associated with these streams produces small but real fluctuations in the local dark matter density and velocity distribution. If direct detection experiments ever do see a clear signal, those streams should leave imprints on the signal that could be used to study the dynamical history of our galaxy. There is also the possibility that dark matter is not perfectly smooth, even on the smallest scales. In the simplest models, dark matter halos contain not just diffuse particles, but also clumps, small subhalos that have survived the disruption of larger structures and are drifting through the larger halo. Some of these clumps may be massive, others microscopic. If small clumps of dark matter happen to pass through the Earth, they could produce brief, anomalous signals in dark matter detectors, signals that would look like brief flashes, rather than the smooth modulation expected from a uniform background. None of the current experiments has reported such a signal, but the sensitivity to clumps depends on detector size and on the rate at which clumps pass through. Future experiments may be able to test these scenarios directly. This is one of the more imaginative directions in current dark matter research. If the dark matter clumps in our halo extend down to small scales, perhaps even to scales smaller than planets, then the Earth might occasionally pass through a small clump. The transit would be brief, perhaps lasting hours or days. But during the transit, the local dark matter density would be temporarily higher than usual, and a sensitive enough detector would see an elevated signal rate. No such transient signals have been confirmed. But the limits are still being refined, and several research groups are looking systematically at the historical data from existing detectors to see whether any unexplained brief signals might be candidates for small clump transits. The search is reminiscent of an earlier era of astronomy, when patient observers looked for transient phenomena in the sky that might be the signatures of unknown objects passing through the solar system. Now the search is conducted in deep underground laboratories, looking for transient signals in the data streams of cryogenic detectors. The principle is the same. The physics of dark matter passing through ordinary matter is, when one thinks about it carefully, very strange. Through every cubic centimeter of your body, at this moment, perhaps 100 million dark matter particles are passing every second if dark matter is made of WIMPs of typical mass. The number could be larger by orders of magnitude if dark matter is made of lighter particles. If it is fuzzy dark matter, you are immersed in a single coherent wave that ripples gently as you move through it. Whatever it is, it does not stop at the surface of your skin. It does not stop at the surface of the Earth. It does not stop at the core. Dark matter particles enter the Earth from one side, pass through about 13,000 kilometers of rock and iron, and emerge on the other side as if nothing had happened. Some of them collide with atomic nuclei along the way, but the rate is so low that, on average, only a few collisions occur per kilogram of matter per year, depending on the model. This is why dark matter detectors must be so large and so sensitive, to catch the few rare collisions out of the trillions of particles that pass through them unnoticed every second. The flux of dark matter through the Sun is even more remarkable. The Sun, in its orbit around the galaxy, has been sweeping through the dark matter halo for 4.5 billion years. Some dark matter particles, passing through the Sun, scatter off the protons in its hot interior and lose enough energy to become gravitationally bound to the solar system. Over billions of years, a small population of dark matter particles has accumulated inside the Sun, trapped by the gravity of the central mass. They orbit through the solar interior, occasionally annihilating with other accumulated particles, producing neutrinos that escape into space. The IceCube Neutrino Observatory at the South Pole has been searching for these neutrinos, and the absence of any clear signal from the Sun has been used to set limits on dark matter properties. So far, the Sun has refused to reveal a dark matter signature, but the search continues. There is a more speculative possibility, less well tested, that the same accumulation might occur in any large mass over long enough time. If dark matter particles can be slowed and captured by ordinary matter, then planets, stars, and even larger objects in the universe might build up dark matter cores over their lifetimes. Some calculations suggest that very old stars in dense regions of dark matter could accumulate enough captured material to slightly alter their internal structure. The effects, if they exist, would be small. They would show up as tiny shifts in the brightness or temperature of certain kinds of stars, comparable to the precision of modern astronomical measurements, but not larger. So far, no such shifts have been confirmed. But the searches continue in the patient style that characterizes so much of dark matter research. The signal, if it exists, will be small. The instruments will have to be patient. A similar accumulation may occur in the Earth, although on a much smaller scale. Some calculations suggest that over the 4.5 billion years of Earth's existence, a few hundred kilograms of dark matter may have settled into the Earth's interior, trapped by gravity. The total amount is negligible compared to the Earth's mass, but it represents a kind of slow accumulation that mirrors the gradual accumulation of other materials in the planet over geological time. Whether this dark matter affects the planet in any measurable way is unclear. Some speculative theories suggest that dark matter annihilations in the Earth's core could contribute a tiny amount of heat to the Earth's interior, but the contribution, if it exists at all, would be far below what is currently measurable. The physics of dark matter at human scales is strange in another way. The substance is not just abundant in the universe. It is abundant here, now, in this room. The room contains, by mass, more dark matter than dust. More dark matter than carbon dioxide in the air. Far more dark matter than any of the trace elements that natural science has named. The total amount in a typical bedroom is small in absolute terms, perhaps a few thousand particles at any given instant if we are imagining WIMPs. But it is non-zero, and it is present, and it has been streaming through the room since long before the room existed. The walls do not stop it. The floor does not stop it. The roof does not stop it. There is no shielding from the dark matter wind, and there never will be, until and unless we learn what the dark matter is and find a way to interact with it more strongly than gravity allows. There is something philosophically interesting about this. Most of the matter in the universe is here, with us, all around us, passing through us, and we cannot feel it. Our senses, our skin, our nervous systems, our entire biological machinery are blind to it. We evolved to perceive the things that interact with light and ordinary atoms, because those are the things that affect our survival. Dark matter does not affect our survival in any direct way. It is irrelevant on the timescales of human life. And so we have no sense organ for it. It is, for us, as though it were not there. But it is there. It accounts for most of the matter in the universe. It built the structures we live in. It has shaped the galaxy that contains us, the cluster that contains the galaxy, the supercluster that contains the cluster. It is the deeper substrate of our reality, and we walk through it without knowing. This is one of the most genuinely strange facts about the universe as currently understood. The world we perceive, the world of light and atoms and chemistry and biology, is the minority world. The majority world, the dark sector, lies behind it and around it and inside it, present everywhere, perceived nowhere. The dark matter is not far away. It is here. It is now. It is in this room with you as you watch this, and we still do not know what it is. The history of dark matter summarized in a single sentence, is this. An astronomer in the 1930s noticed that a cluster of galaxies seemed to be too heavy. For 4 decades, no one took the results seriously. Then, in the 1970s, a different astronomer showed that every galaxy ever measured was also too heavy, in exactly the same way. The evidence from gravitational lensing, from the cosmic microwave background, from the formation of cosmic structure, and from colliding clusters has, in the half-century since, accumulated into one of the most thoroughly established facts in modern science. The universe contains a vast amount of matter that does not emit, absorb, or reflect light. 5/6 of all the matter in the cosmos is of this kind. And despite 4 decades of intensive searching, in detectors built deep underground, in space telescopes, in particle accelerators, in radio observatories, in giant magnets and ultra-cold crystals and arrays of liquid xenon, we still do not know what this matter is made of. The current state of the search is a kind of focused frustration. The leading candidate, the WIMP, has been pushed to the edge of plausibility. The remaining region of parameter space in which standard WIMPs could exist and remain undetected is small and getting smaller every year. The detectors now being built, due to begin operations later this decade, will cover most of what remains. Within the lifetime of anyone watching this video, the WIMP hypothesis will be either confirmed or, more likely, definitively ruled out. The same is true for axions. The leading axion search, the ADMX experiment, is steadily scanning through the range of possible axion masses. So are several other dedicated axion detectors. The masses that current theory considers most plausible are being covered now. Either an axion will be detected in the coming decade, or the simplest axion models will follow the WIMPs into the museum of ruled-out ideas. If both of those happen and no signal is detected by either program, the field will face a genuinely difficult moment. The 2 most theoretically motivated candidates, the 2 ideas that have driven dark matter research for the past 40 years, will have run out of room. The community will have to turn, in earnest, to the more exotic possibilities. Fuzzy dark matter, primordial black holes, sterile neutrinos, hidden sector models with multiple species and forces, and ideas that have not yet been imagined. Some of these are already being investigated. Others wait in the wings. The field will not stop working on the problem. Dark matter is too important, too central to our understanding of the universe, to give up on. But the easy paths will be closed, and the difficult ones will have to be walked. There is also a possibility that some physicists have always taken seriously, which is that the problem is harder than it looks because the dark sector is not simple. What if the dark matter is not a single particle or even a small family of particles, but a rich and complex set of fields and forces, fully as elaborate as the standard model of ordinary matter, but completely hidden from us because it does not couple to the ordinary world except through gravity? In this picture, there might be many different kinds of dark matter, with different masses and different properties contributing to the cosmic budget in different ways. The search for a single particle would never succeed, because there is no single particle. There is a whole world we cannot see, layered into the same space we inhabit, with its own structures and its own dynamics. Whether this picture is true is, at the moment, unknown. But it cannot be ruled out by current observations, and it remains a serious theoretical possibility. What is striking about all of this is how the case for dark matter has grown more secure, as the case for any particular candidate has grown less so. 40 years ago, we were nearly certain that dark matter must exist, and we had strong theoretical reasons to expect it would be a WIMP. Today, we are even more certain that dark matter must exist, but we have far less idea of what it is. The evidence for its existence, from every direction in cosmology, has only solidified. The evidence for any specific identity has, if anything, weakened. The substance is more real, and more deeply mysterious than it was when the search began. There is something striking about the contrast between the precision of what is known and the depth of what is not. The total mass of dark matter in the universe is known to within a few percent. Its distribution is mapped across the sky in unprecedented detail. Its behavior, on scales from individual galaxies to the entire observable cosmos, follows the predictions of theoretical models with remarkable accuracy. Cosmologists can tell you, with confidence, how much dark matter was in any region of the universe at any moment in cosmic history, going back to the first few 100,000 years after the Big Bang. They can tell you how it clumped, how it shaped the formation of stars and galaxies, how it built the cosmic web that contains us. They can do all of this without knowing what a single particle of it looks like. The picture is detailed and precise and almost complete, with one enormous gap at its center, the gap where the identity of the substance should sit. In the history of science, there has rarely been a comparable situation. The closest analogy might be the period in the 19th century when chemists had learned to identify the elements in detail, knew their relative abundances, and could predict their behavior in countless reactions, all without knowing what atoms actually were or whether they existed at all. That gap was filled, eventually, by Einstein and Perrin and the experimental confirmations of the early 20th century. The dark matter gap is, perhaps, in a similar position now. We know what it does. We do not yet know what it is. The filling of that gap, when it comes, will be one of the most important moments in the recent history of physics. This is not a failure of physics. It is the way science actually works. The history of 19th century chemistry was the history of slowly cataloging the elements, finding new ones, ruling out wrong ideas, refining the picture year by year. The history of 20th century particle physics was the history of identifying, one by one, the fundamental particles that make up ordinary matter. The history of 21st century cosmology will probably, in retrospect, look like the history of identifying what dark matter is. The work is not finished, but the work is being done. The problem is not abandoned. The problem is, in fact, the most active and intensely pursued problem in physics today. What does dark matter mean for our place in the universe? In one sense, very little. The dark matter does not affect the chemistry of life, the physics of stars, the geology of planets, the weather, the climate, the orbits of moons, the trajectories of spacecraft. It is gravitationally important on the scale of galaxies, and larger, but on every smaller scale, it is essentially absent. The matter that we are made of, the matter that builds the visible cosmos, behaves as it always has. The discovery of dark matter does not change the way the world looks from a human point of view. The sun still rises, the trees still grow, the seasons still come and go. But in another sense, dark matter changes everything about how we understand our place. For most of human history, we assumed that the visible world was all there was. We cataloged it. We described it. We built theories of physics that, with extraordinary success, accounted for the behavior of every kind of matter we encountered. And then, in the 20th century, we discovered that the visible world was a tiny minority of what actually exists. The cosmos we can see, the cosmos that includes every star, every planet, every galaxy, every cloud of gas, and every clump of dust, is only one part in 6 of the total matter content of the universe. The rest is a different kind of matter, made of unknown substance, behaving according to unknown rules, and surrounding us at every moment. We are, in a literal physical sense, surrounded by something we cannot identify. We do not understand the majority of the matter in the universe. We understand only the small visible fraction. This is a humbling situation. It is also an exciting one. The history of science is, in many ways, the history of discovering that the world is larger and stranger than we had assumed. The Earth was not the center of the universe. The Sun was not the center of the galaxy. The Milky Way was not the only galaxy. Each of those discoveries reshaped our understanding of our place. The discovery of dark matter is in the same lineage. The visible universe, the universe of stars and planets and life, is not the whole universe. It is the brightly lit foreground of a much larger and darker structure, the cosmic web of dark matter that built the galaxies and that holds them in place. We live inside the bright foreground. We do not yet know how to perceive the rest, but it is there. What will happen next? Probably this. Over the next 10 to 20 years, the experimental programs will run their course. WIMPs will be detected or ruled out. Axions will be detected or ruled out. The Rubin Observatory and other survey telescopes will produce maps of the dark matter distribution at unprecedented precision, allowing fine details of dark matter behavior to be tested against theoretical models. New experiments will be built. Some will succeed, most will not. The field will continue, as it has continued for the past half-century, through a combination of incremental progress and occasional breakthroughs. Whether the answer comes in the next decade or the next century, it will come. Because the universe is consistent and the universe contains dark matter, and dark matter must, somewhere, be findable. In some ways, the experimental program of the next decade is more diverse than any that has come before. Direct detection experiments will scan deeper into the WIMP parameter space, probing interaction strengths millions of times weaker than the original searches could reach. Axion detectors will cover the most theoretically motivated mass ranges, working their way through the parameter space frequency by frequency. New experiments will look for dark matter candidates that fall outside the WIMP and Axion frameworks, including hidden photons, ultralight scalars, and forms of dark matter that interact with ordinary matter through forces that have not yet been cataloged. The Cherenkov Telescope Array, beginning operations in the late 2020s, will look for high-energy gamma rays from dark matter annihilation in the cores of dwarf galaxies, with sensitivity orders of magnitude better than its predecessors. The Square Kilometer Array, the largest radio telescope ever built, will produce maps of the cosmic web and the intergalactic medium that will test predictions about how dark matter influenced the formation of the first stars. Each of these instruments addresses a different version of the question. Each is built to test a different range of possibilities, and together they cover, for the first time, most of the theoretical landscape that the field has produced over the past 50 years. The list of major experiments and observatories is now long enough that the field could not be summarized in a single video. There are the underground dark matter experiments with their cryogenic crystals and their tons of liquid xenon. There are the Axion experiments with their giant magnets and their listening receivers. There are the space telescopes mapping the cosmic microwave background and the large-scale structure of the universe. There are the ground-based survey telescopes, photographing billions of galaxies and inferring the dark matter distribution from gravitational lensing. There are the radio telescopes, listening for signatures of dark matter interactions in the early universe. There are the particle colliders, looking for missing momentum in their collision debris. And there are the theoretical physicists, building models that would link the dark sector to the standard model of particle physics, looking for clues in the patterns of what has and has not been found. The dark matter problem is no longer a problem any single experiment or single approach can solve. It has become a problem that requires the full machinery of modern physics, deployed across multiple wavelengths, multiple energies, and multiple scales, all looking for the same elusive substance. When the answer comes, it will, in a single moment, transform the picture. A new kind of matter, finally identified and characterized, will become part of the standard physics curriculum. Textbooks will be rewritten. The cosmological story will be updated. Particle physicists will move on to the next question, which is probably the question of dark energy, an even more mysterious component of the universe that we have not addressed in this video. The dark matter will, at that moment, cease to be a mystery and become a fact. The transition from one to the other will be quiet, in the way these things usually are. The press conference will be held. The Nobel Prize will be awarded. And then the universe will look slightly different than it did before. Slightly more comprehensible, slightly less hidden. We are not at that moment yet. We may not be near it, but every observation made, every detector built, every theoretical model proposed, every map drawn of the cosmic web brings the moment incrementally closer. The work continues, in deep mines and at high altitudes, in laboratories and at telescopes, in the careful patient grinding of a problem against the patient grinding of the world. The answer will come. For now, what we have is the strangeness itself. The Milky Way is not what it appears to be. The galaxies we see are not the galaxies that exist. The empty spaces are not empty. The room around you is not as quiet as it looks. The universe is heavier, denser, and more populated than every appearance has suggested for most of human history. And the matter that fills it is matter we have not yet learned to perceive. Somewhere right now, in a laboratory in Italy or South Dakota or China or at the South Pole, a detector is running. A graduate student is checking the data from the latest shift. A physicist is sitting in front of a screen, looking at a histogram, hoping to see a small bump that is not background. Tomorrow they will check again. The next year they will check again. At some point, sooner or later, the bump will be there. The signal will appear. And the longest-running mystery in modern physics will be one mystery shorter. Until then, the dark matter remains what it has always been since Zwicky first noticed that the coma cluster was too heavy. Present in vast quantities, detected only by its gravity, mapped across the cosmos, untouched in any laboratory, holding galaxies together, holding the universe together, real, abundant, and unknown. There is one more thing worth pausing on before this video ends. The dark matter problem, taken in its full scope, is a reminder of how much of physics has yet to be done. For most of the 20th century, physics felt close to complete. By the end of the 1970s, the standard model of particle physics had achieved an extraordinary degree of consistency. The fundamental constituents of matter were identified. The forces between them were described. The experimental tests were all coming back positive. Some physicists believed briefly that fundamental physics was approaching a kind of completion, with only details left to fill in. The discovery of dark matter, and a few years later the discovery of dark energy, ended that optimism. It became clear that the standard model, however well it described what we could see, was an incomplete description of the universe. The matter and forces of the visible world were only part of the picture. There were other things, gravitationally important, completely invisible, that the standard model did not contain. In the half-century since, the field has been digesting this fact. The standard model has not been discarded. It still works extraordinarily well for the matter that humans, planets, and stars are made of. But it is now understood as a partial description, the part of a larger structure that happens to be visible. The dark sector is something the standard model does not include. Its discovery, whenever it comes, will require extending the model, adding new particles and new forces and probably new principles. And this extension will be one of the most important developments in the science of the next century. The work of doing this is happening now. As this video is being recorded, hundreds of physicists are running experiments designed to constrain or detect dark matter. Thousands more are working on the theoretical models that frame the searches. Across continents and across disciplines, the dark matter problem occupies the attention of a generation of scientists who have grown up with it, who have come to understand it as the central unfinished problem of cosmology, and who are dedicating their careers to the question of what it is. The work will continue for as long as the question remains open, and the question will remain open until the answer arrives. When the answer does arrive, it will reshape our picture of the universe in ways that are difficult to predict. Perhaps it will be a single new particle, slotting neatly into a slightly extended version of the standard model. Perhaps it will be a whole dark sector with its own particles and forces and structures. Perhaps it will be something stranger still, something none of the current candidates have anticipated. Whatever it is, it will change the way humans think about what the universe is made of. The cosmos we inhabit will be revealed, more clearly than ever before, to be a place whose visible features are the surface of something deeper. The dark matter is the floor of the room we live in. We have not yet looked under it. When we do, we will see what holds the universe up. If you enjoyed this exploration of one of the deepest unsolved questions in modern science, a like or a subscribe helps us continue making them. The universe still has plenty left to reveal, and we will be following it as it does.